Welcome to Haaker Equipment Company. We are a municipal equipment dealership. We have two locations, one in the city of Laverne covering Southern California, and one in Las Vegas that covers the Southern Nevada area. The manufacturers that we represent are Vactor and their 2100 plus sewer cleaning model, the HXX hydro excavator, along with other models that will clean or dig with the use of high pressure water and air conveyance. In this class, we'll talk about flow and pressure, nozzles, the care of rod or hose, and proper setup. Hello, my name is Kerry Alcott. I would like to start out by asking a question. I see a lot of operators when jetting a line. They will go up the line at a pressure around 1,800 pounds per square inch, showing on the pressure gauge on the hose reel. Then when they pull back, they lower the pressure to around 1,200 psi or more. Why are they doing this? They're doing this so not to blow up a toilet. So they think. The reason for a toilet to bubble over is caused by three things. One is air pressure pushing water out of the trap at the toilet. Two, there is also a sucking a toilet down, which is caused by poor ventilation from the roof vent of the house when the nozzle in the line is coming to the lateral. 3. An overfull line pushing water up the lateral. Let's look at these theories by drawing some pictures and using a little common sense. Here we have a typical house that belongs to the Jones family. Their lateral connects to the line in the street. In front of their house to that lateral is a cleanout. Let's take a look at their plumbing to understand how it works. The lateral connects to a soil stack that goes up to the roof, called the roof vent. All of the sinks, baths, and toilets have a trap that holds water. The water is necessary to keep sewer gases out of the house and is vented to the roof. When water is ran in a sink or a toilet is flushed, the roof vent allows air to enter and water to flow down and not create a siphon pulling all the water out of the trap. What happens when we clean a line? Here is an 8-inch diameter pipe in the ground. This line has a normal flow of 1/4 to 1/2 full. Now let's put a nozzle and a hose in the line. This will pull water from in front of the nozzle and add more flow behind the nozzle. This is a front view of our nozzle in the line. Let's add a house. A lateral, and this lateral has a cleanout, and out of the roof is the vent. As water comes out of the nozzle in the confines of a pipe, the water movement flow brings a lot of air with it. A question: where does the air come from? Answer: it comes from the lateral that is attached to the roof vent. Let's say this house has a restriction in the roof vent. We have air being pulled from this house with a restricted vent, so the least path of resistance is the traps. This means we could pull water out of the toilet and upset this house. To avoid this, if there's a history with this house, we could open the cleanout and allow air to enter the lateral before the house. Or We can open the manhole we are jetting to and let a large amount of air enter the system so we are not pulling from any house. Our nozzle is now past the lateral. On the back side of our nozzle, we have the water we pulled from the front of the nozzle that was in the line and the air we are moving, plus we are adding water and filling up the pipe and forcing the air to compress, and it needs to go someplace. Where does it go? It goes back up the lateral. And if the vent has a restriction, then the water is pushed up the toilet and upsetting the house once again. Okay, let's do a little recap. When coming to a lateral, we are pulling air down the lateral, and after we pass the lateral, we are pushing air back up the lateral. So there's like a little recoil happening, and that could cause water to push from the trap out of the toilet. Both water and air are flowing down the pipe. As we increase the flow of water, like a larger nozzle, we also increase airflow. We also fill the pipe with more water. As we pull our rotor hose, we are cupping what is behind the nozzle and pulling it down the line. If we increase the speed of our pull, we bring more water with us faster. If there is more flow and speed added, could we accumulate so much water to overfill the pipe and send it up the path of least resistance, the lateral? Have you ever watched the water flow below you in the manhole as you jet and see a surge of water shoot out of the pipe opening? Is that water pressurized or pockets of air escaping? How far up the line is your nozzle at the time you see the surge? How far up the line did all of this water start to be pressurized? How many laterals are there in between? And now we have to explain to Mrs. Jones what just happened. Things we can do to help prevent this from happening. We can open the manhole upstream to let air enter the system. We can open the cleanout at the house that has a history of toilet blowups. We can bring the hose back at a slower speed. We should see in the manhole below us a steady stream of water moving. It will be an increase of flow than what there was, but no surges. We can use a smaller gallons per minute nozzle to reduce water flow, and when we reduce water flow, we will reduce airflow in the line. Question: what do we need to clean a line? Answer: we need flow to carry the debris downstream. The lower the flow that's in a line, the more flow we have to add to get the debris down the line. That means using a larger gallon per minute or flow nozzle. What else do we need to clean a line? We need pressure to break any scale off the sides of the pipe or break roots. We need pressure to cut grease. If we have too little of pressure, we won't get the line clean. If the line has plenty of flow, why add more water and waste it? That means using a smaller flow nozzle. We need pressure to break the scale and cut the roots and the grease. We need the flow to carry the debris downstream. We need pressure and flow to climb up hills and go further down a long line. This is called thrust. Thrust is what pulls the nozzle and the hose to where we need it. Thrust is what moves the debris down the line, but it increases airflow. One nozzle cannot do it all. The nozzle is what determines flow. The size of the orifice and the number of orifices determine that flow. Pressure is created by the flow forced through an orifice, called restriction. The smaller the orifice at a set flow, the higher the pressure. Remember that the orifices can wear out, get bigger in size. This will cause an increase of flow and engine RPM to try to regain the pressure. Using a smaller flow nozzle can do the following for us. It can make our water in the truck last longer. It will reduce the airflow through the pipe. It will lower engine RPM, which will save fuel cost and noise of the engine. And that will lower the temperature at the front of the truck. Here is a chart to give you an idea how long your water will last with different size nozzles. Our common nozzles are 80 and 60 gallon a minute. But what if we ran a 40 gallon a minute nozzle? Like we said, we can reduce the flow of air, save water, run higher pressures for better cleaning, as long as there's good flow to carry the debris away, and don't need thrust for long lines or hills. Question: if the operator lowers the pressure to 1200 psi to keep from blowing up a toilet, does he have 1200 psi cleaning the line? Let's talk about friction in the router hose, also called pressure drop. Let's first take a look on how much flow can a hose handle. The common sizes we use are 3/4 inch and 1 inch hose. 3/4 inch hose can handle up to 50 gallons a minute, and a 1 inch hose can handle up to 80 gallons a minute. Pressure drop in a hose. Pressure drop is due to friction. The greater the flow in a hose, the more pressure drop there is. The smaller the diameter of the hose, the more pressure drop there is. And the longer the hose, the more pressure drop there is. This is a fluid flow pressure calculator that you'll find at gates.com. This is a calculator that shows what pressure drop is in different hose IDs and lengths. This information is from the Gates calculator. We'll show different scenarios for 1 inch hose. The first chart shows 1 inch hose, 600 foot length at 80 gallons a minute. Now look over at pressure loss. It is 968.7 pounds total, or 1.6 pounds per foot. The next chart, same ID and length, but at 60 gallons a minute. The pressure loss is 558.9 pounds, or 0.9 pounds per foot. And at 40 gallons a minute, the pressure loss is 258.5 pounds, or 0.4 pounds per foot. Okay, for every 20 gallons a minute, we lose 1/2 a pound per foot. This chart shows different scenarios for 3/4 inch hose. The chart shows 3/4 inch hose at 600 foot length, but at 50 gallons a minute. Now look over at pressure loss. It is 1,620.42 pounds total, or 2.7 pounds per foot. In the next chart, same ID and same length, but at 40 gallons a minute. The pressure loss, 1,057.68 pounds, or 1.89 per foot. And at 30 gallons a minute, the pressure loss is 612.75 pounds, or 1 pound per foot. Okay, for every 10 gallons a minute, we lose 3/4 of a pound on 3/4 inch hose. This chart shows different scenarios for 1 inch hose lengths. All the same gallons per minute, but different lengths of hose. Notice the pressure drop per foot stayed the same, but the total pressure is higher with length. Okay, do we really need 800 feet of hose on our machines? This is a comparison of 3/4 inch to 1 inch hose. 3/4 inch hose at 400 feet has a pressure drop of 1.8 pounds. 1 inch hose at 60 gallons a minute is still less at 0.9 pounds per foot. Alright, if we only need 400 feet of hose to do the job, and we ran 40 gallons a minute, we would have 0.4 pounds per foot. What the operator needs to understand is that the reading at the hose reel gauge is not the pressure at the nozzle. That GPM is the same as flow. Pump pressure, pounds per square inch, at the hose reel, not at the nozzle. And pressure drop in the hose is affected by diameter of the hose, length of the hose, and the amount of flow through the hose. Let's go back and think about the original question. Jet up the line at a pressure around 1800 psi. And coming back, they lower the pressure to around 1200 psi or more. When we lowered the pressure to 1200 psi, how much pressure do we have at the nozzle? Yes, we lowered the flow also, but we might only have 400 to 800 pounds of pressure doing the cleaning. In shallow residential lines, use a 40-gallon-a-minute nozzle at high pressure, around 2000 psi. This will clean the line better, it will reduce airflow in the line, and will save water. It will allow the truck to run at a lower RPM, and that will save fuel, and allow the truck to run cooler, and less engine noise for you, and will reduce toilet blowups. Thrust, as it is utilized in the sewer cleaning operation, is a measurement of the forward force produced by the rearward discharge of water. This chart shows how much thrust at different flows and pressures. Look at the yellow highlighted area. By doubling the flow gives us a 100% increase of thrust. Where below that, we see by doubling pressure only increases thrust by 41%. Increasing water flow and pressure will increase the nozzle's forward movement, called thrust. Thrust is needed more for going up hills or long pipelines. And higher thrust will increase airflow. Things to think about. Have you ever run a line and can't get more than 300, 400 feet and the hose stalls? Not enough thrust. You need a larger gallon per minute flow nozzle. If I only put 400 feet of hose on my truck, I could store 200 feet and put it on when I need it. Do you have an easement machine? That would be a way to store hose. I would have less pressure drop with 400 feet of hose to feed an easement machine. Have you ever pulled a hose back and out of the pipe in the manhole below you, you see water shooting or surging out of the pipe? Air is being pressurized by water and air filling up the pipe behind the nozzle, and the nozzle pulling more water back than what the pipe can handle. If there was a lateral between you and the nozzle, we could have just use a smaller GPM or flow nozzle and pull back. NASCO, the National Association of Sewer Service Companies, is committed to setting industrial standards for the assessment and rehabilitation of underground pipelines and to assure the continued acceptance and growth of trenchless technologies. NASCO has set standards for nozzles to classify designs into tiers. Tier 1 is a basic nozzle. Made from mild steel, hardened steel, or stainless steel. They have drilled orifices, making them disposable. Fair to poor fluid mechanics, they are the most common in the industry. Tier 2 nozzles. More durable. Replaceable orifices with fair to good fluid mechanics. Tier 3 nozzles. Replaceable orifices, excellent fluid mechanics, the highest performance. These are all cleaning nozzles. They have rear jets for thrust and cleaning, and some may be adapted with a forward jet to help penetrate a blockage. This cleaning nozzle has forward jets for cleaning laterals or cleaning on a downhill grade. Jetting angles. In a pipe and a centered nozzle, from the center of that nozzle, jetting orifice angles vary from 15 to 40 degrees. A 15-degree angle will push debris further downstream in a flat pipe. This angle will develop more thrust for climbing hills. This angle will shoot past a lateral better, but won't clean the sides of the pipe as well as a 30-degree. Will increase airflow. A 30-degree orifice will contact the side of the pipe more directly and apply more pressure for better cleaning. Will have moderate thrust and will be more direct towards the lateral opening. Some nozzles have a combination of 15 and 30-degree orifices. Dual angle nozzles give you better cleaning with more thrust. Here you can see the two angles. Notice the contact of the lateral and how much water is coming back out. Yes, there is infiltration at this joint. Penetrating nozzles. There are rear jets to get down the line and forward jets to cut through a blockage. Some penetrators are shaped like a chisel. Some with a drilled tip to help cut the blockage. Finishing or polishing nozzles. These nozzles have a center barrel that spins at a high rate of speed. There are rear jets to get down the line. The center barrel has one jet to do the cleaning and to propel the spinning action of the barrel. There is a second jet at a different angle to slow the barrel down to help clean. If we didn't slow the barrel rotation, it would spin so fast that the water would bend, losing force to the side of the pipe. Floor cleaners. Used in large line cleaning and in storm drains to remove gravel and big rocks. The floor cleaners have jets pointing to the rear bottom of the pipe only. There will be a swivel joint so the hose does not turn the nozzle over. A roll cage if it does roll over, and it's weighted on the bottom so it will upright itself. There are replaceable wear skids to protect the body. The fill port is for adding weight to help stay underwater in high flow pipe. And it will have a ramped up nose to elevate the front to change the angle of the rear jets as it goes over debris. Chain flails. For roots, scale, and hardened materials. The chain flail with properly adjusted skids centering the nozzle in the pipe and the chain adjusted to the correct length, this nozzle is very efficient in cleaning tough materials. Rotor hose. Rotor hose is made from thermoplastic, and there are 3 layers. The inner layer is color-coded to identify the manufacturer of the hose. The middle layer is the strength of the hose, made of woven cloth. And the outer layer protects the middle layer and identifies the working pressure of the hose. The color of the inner liner IDs the manufacturer, so if the black writing wears off the outside of the hose, we will know who made it. The blue liner IDs Aeroquip as the manufacturer, and yellow IDs Piranha as that manufacturer. Some examples of other manufacturers are gray is for Parker and orange is for Dynaflex. The outer color IDs the working pressure of the hose. The colors and pressures are: orange is 2500 psi, blue is 3000 psi, green or black is 4000 psi, and red is 5000 psi. When repairing the hose, you must use the hose ends and center splice fittings made by the same manufacturer as the hose. And you must use the tools from that manufacturer as well. Notice everything is color-coded for easier identification.
A Piranha-supplied swedging machine is required for the installation of end fittings and menders. All assembly tooling is designed and produced specifically to be compatible with the Piranha Hose Products supplied swedging machines and hose. We have available 2 types of swedge machines. These machines can be used to assemble Piranha sewer cleaning hoses from a 1/2 inch up to 1 inch. Please call Piranha Customer Service for information on assembly and repair of the Piranha 1¼ inch hose. The hydraulic non-electric swedge machine operates by a pump-action hydraulic system and is easy to use. The horizontal swedge tool is a manual unit which is handy for in-the-field mobile units. We'll be using both machines in our demonstrations. Let's start with the hydraulic swedge machine and assemble an SP16 1-inch Piranha sewer hose with a 1-inch Piranha male end fitting. You'll also need some other equipment: a marking pen, sharp knife or other cutting tool, measuring tape or ruler, a water-soluble soap solution, oil lubricant, a wrench, rubber mallet, Piranha assembly repair sheet, and safety glasses. First, cut off the old end fitting about 1 foot from the end, using a sharp knife, making sure the cut is as square as possible. Mark the insertion depth on the hose. You can do this by referencing the insertion depth chart on the Piranha assembly sheet. Measure with a ruler. Mark the hose with the marking pen. This will be the end point of insertion for the fitting. Prepare the hose and hydraulic swedge machine, using 1 set of dies and the pusher, making sure that they match the size of hose that you're assembling. Insert the die set in the bottom of the machine and lubricate the inside of the die. Slide the Piranha end fitting onto the end of the hose. You may use a water-soluble soap solution to assist you, as the fit must be tight. Do not, however, use oil to assemble the fitting to the hose. Insert the pusher in the top of the machine. Push the fitting and hose up through the die set and to the pusher, making sure the threaded end is going into the pusher. Using the provided handle, pump the jack until the die and pusher depress completely together. Release the jack, and with the rubber mallet, tap out the die set and pusher from the machine, doing the same with the Piranha end fitting. Check that the hose end is secured to the hose. Inspect the hose looking for the following. There is no hose movement in the male end fitting. The hose insertion mark on the hose is still located at the end of the male end fitting. The hose is ready to use if it is free of any other damage. To mend a hose using the hydraulic swedge machine, the process is the same, except you'll be using 2 sets of dies and a mender, inserting the second die set in place of the pusher and the mender in place of the male end. WasteTech recommends that no more than 3 menders be used on any one length of hose.
Damaged hose. Repair your hose for any of the following reasons. Cover damage is from wearing on the pipe, and if the woven cloth is exposed and frayed, the hose can burst at lower pressures. Burst could have occurred from damage to the outer cover or cracking of the inner liner. Bubbles and blisters is caused from inner liner damage and pressure leaking out to the inside of the outer cover. Kinking and collapsed from bending too tight or driving over the hose. A suggestion for longer life out of your hose: rotate the hose. If you have a second sewer truck and when it's time to replace a roll of hose, you could put the hose from the second unit on the unit you take the hose off of. This will put the used end of the hose to the inside of the other reel, and the end with very little use will be on the outside. Proper setup. A leader hose serves 2 purposes. One is length for safety, to know when the nozzle is coming out of the hole. You should have a leader long enough to see a color change within 3 feet of the top of the manhole and still be in the line about 3 feet. Second, the leader is a section of hose that will wear due to abrasives behind the nozzle. A longer leader will help protect the thermoplastic hose. Nozzle support is a length of pipe that goes between the leader and the nozzle. The main purpose is so the nozzle does not make a U-turn in the pipe or go where we don't want it to go. The second reason is to center the nozzle in the pipe for more even cleaning and so the nozzle doesn't wear on the bottom of the pipe. What is showing is called a proofer. That is about a ½ an inch smaller ID in the pipe. If this goes up the line and back without stopping, it proves that the pipe is in sound condition as far as any restrictions. Hose protection. Use a device like a tiger tail to protect the rod or hose from damage. This will be placed in the opening of the pipe, so when the rod or hose is pulled out, that the outer layer of the hose does not get cut on the edge of the pipe. I hope this information has been helpful, and thank you for your attendance. If you have any questions or would like to comment on this video, you can contact me by email at carrio@haaker.com.